So welcome everyone to our second day of the workshop. And currently I see 29 people, probably some will connect also. And we will continue what we started. Thank you. Thank you very much for kind words. Today we will also speak more about quantum stuff than yesterday. I want also to inform you about two events that will happen during today's meeting. First of all, I will add some 10 minutes of break closer to 3 o'clock so that we won't be doing everything in one sitting, so you will have time to rest a bit and refresh your mind. And second, when I will finish going through all the notebooks, we will have quizzes. And for that purpose, I will share screen. Actually, I should have started doing it earlier, I guess. So now you probably see my Discord server. Yeah, I even received notification participants cannot see your application. So here is quiz channel, and here I will publish the quiz. It will be consisting of questions, and there will be also options for answers given, and you would need just to pick the right answer. And for answers, you will get points, and so it will be like a small contest. It will not affect diplomas or any other bonuses. It is just for fun, but you may also become famous. Now let me switch to the content. So we are back to our materials. And before I start, maybe some of you have any questions regarding what we did so far yesterday. If you have any questions, please let me know. Oh, I see there is one question, and I guess it was from also published one moment in Discord. So coin flip notebook 8. So it is related to one of the first programming tasks. All right, so we pick n as precision of our probabilities. I can explain you why, because at the end we'll have even number of options. As you have seen, rand range returns to us any number between 0 and n minus 1. So you remember, if I put rand range 2, it will output random number between 0 and 1. Oops. Okay, we can use also this one. You remember this example. So if we have number 2, we'll get 0 or 1. Here, what we wanted to do, it is not exactly odd number. It is, more precisely speaking, it is 10 to some power. So like 10 to the power of k plus 1. If you have rand range with such number, so rand range, it is in correct code. I just show you the idea. So if you have here such number, then you will get any number between 0 and 10 to the power of k. And this is what we want to do, because 0 will represent probability 0, and 10 to the k will represent probability 1. So if you have rand range from 10 to the power k plus 1, it is much easier to manipulate with these numbers. So this was the main reason why it was solved in this task. I hope I answered your question. So it is not exactly about odd number. It is about having precision being some 10 to some power. And we needed to add 1 just to technically ensure that this one is giving us exact possibility. Yes, it is simplification. So here we program biased coin, but at the same time we program this precision in decimal numbers. And so if you have run range (1001), then you will have options of these numbers. And this would be 0%, this one 0.1%, and this one would be 100%. Or alternatively, as we write our probabilities, thank you for asking. So yes, it is simplification, and this is what we get. Much easier to manipulate with such numbers. All right, then we'll transition to our materials. And we have finished up to this point. Now we will speak about basics of quantum systems. And I will just in case switch off the camera so that those who have a bit weaker internet connection will save a bit traffic. So we will speak today only about constructions involving single qubit mostly. And we will learn all the operations that we can perform on it. Keep in mind that this is bronze course, so it is also a bit simplified, that we do not consider complex numbers. So we only consider the cases when all our qubits can have amplitudes being real numbers. But you will see also there is a lot of things that we can do with it. So here we return to our coin flipping experiment, and quantum operator that will represent this coin flipping. You remember from previous lecture, coin flipping was represented as beam splitter for our photons. So this beam splitter was imitating coin flip. Beam splitter flips the photon. So quantum operator that would represent this beam splitter is called Hadamard. And in Qiskit, it is defined as H gate. So we will use letter H to use this operator. We'll implement all three experiments that we have observed yesterday in our notebook about photon coin flipping. Keep in mind that currently we'll consider first and third experiment, and second one we'll check a bit later, but also today. So it is just a warm-up so that to have a bit of experience of quantum programming and experimenting, and later we will have also explanations about mathematical models that is describing quantum computation. So our quantum bit starts in state 0, and we can represent it with column vector like we did yesterday for probabilistic states. So you see, it is state 0. If we think about probabilities, it would be like probability 1 for state 0 and probability 0 for state 1. Later we will learn that it is, in quantum case, not actually a probability, but something a bit different. Currently, just think about the notions that we used for probabilistic systems. Additionally, here is explanation that this bracket, currently you can think just that it is used to represent vectors in quantum mechanics. There also exists conjugate transpose of it, and there is a notion of complex numbers would be needed to explain it. So currently we will use only this notation, we will use ket vectors. So here we build a circuit which will apply Hadamard gate to one qubit. So you have seen code in previous lecture. Here it is quite similar. We import all necessary libraries and objects. We define our quantum register with 1 qubit, classical register with 1 classical bit, and then we define quantum circuit. So these 4 steps is our initialization. Currently, you can copy paste this part in most of the circuits. Later, maybe you will find better ways how you can write it in more well-formed way, but it is one of the possibilities how to write your own quantum program with all this initialization. Next steps indeed depend on the tasks that you're performing. Here we will apply Hadamard gate to the first qubit. So you see indices start from 0 like we're used to in programming for arrays. So we use our register Q where we store our qubits and we say that we are accessing qubit 0. So overall this means we take quantum circuit and apply Hadamard to qubit 0. After that we measure our quantum register and store the results in our classical register. And here we're drawing how it looks like. So you see we have just 1 qubit, applied Hadamard, did the measurement, outcome is stored in classical register. So it is corresponding to our first experiment. You see, we start with photon in state 0, and then we have this beam splitter that is our Hadamard gate. QReg. Oops, quantum. Basically, exactly here, probably your question is about what it is here. Here we define it as a name of register. So this QReg is basically this one. It is technically possible to define several separate quantum registers. So it is intended for more advanced functionality so that if you would have separated your qubits in different registers, then you would be able to just track them by names, like first quantum register, second quantum register, and so on. So QReg here, quantum register that we named here. You're welcome. So here we launch our experiment. These 3 lines of codes also usually will be copy-pasted in the beginning. Not quite. So you see here we have 2 detectors just to be able to distinguish between these 2 cases. So whether we received photon that has been transmitted or the photon that has been reflected. So this is why we use 2 photon detectors, but these 2 photon detectors are related to one single measurement. Yes, you're welcome. So if we launch this code, we will get this information. So as I said, these 3 lines of code also mostly will be copy-pasted by you in the beginning. So it states that if we launched our circuit for 10,000 times, we will get, in this case, state 1 in 5,000 cases and state 0 in a bit less than 5,000 cases. So basically it corresponds to the probability 50-50. You see, now I launched it again, and these numbers became a bit different because probabilistic outcomes can differ from ideal ones. So this is what we get. But it gives us a sense, okay, we get state 0 and state 1 with roughly equal probabilities. What is done here, we just with the code processed this data. So like we counted the number of zeros and ones. So counts is library, counts 0 allows us to access this number. And here we just print it. So what is the frequency? So how many times we have seen zeros from all possible times and multiply by 100%. And so these are percentages that we have obtained. And this is also one of the ways how to represent the outcome. So we see here probabilities for state 0 and state 1. So they're expected to be close to each other, and we managed to obtain exactly the outcomes that we expected. So we had probabilistic output. Now the third experiment, you remember here, we applied one beam splitter and then applied the second one. For the second experiment, I'm not 100% sure, but probably there is such functionality to manipulate with these probabilistic outcomes in Qiskit. So this is where we would need to affect it. We have backend, which is simulating our quantum computation just on your local resources. So it may be possible that there it is, where it is possible to preserve as a result also the probabilistic result. You will see later, actually, there is a way how to show exactly the probabilities. We will learn this already today. There is possibility to output state before the measurement, and it represents as the probability, exact probabilities. So please keep in mind this. Your question will be answered after some 4, I guess, notebooks. How we can preserve exact probabilities. We don't need even to manipulate with seeds. So we skip currently second experiment because it requires also intermediate measurement. It is possible to do it in simulators, but currently quantum machines are not allowing to do intermediate measurements. So what we do here, we now apply 2 Hadamard gates. So you remember, we pass our photon through beam splitter and then pass it again. And so this is what we get. We get 2 Hadamards and measurement. And what will be the outcome? Outcome will be state 0 with 100% probability. So you see, this experiment exactly has been confirmed also on our quantum simulation. So what I want to emphasize with this example, quantum computers initially were meant to simulate quantum physics. This was idea by famous Richard Feynman. In 1982, there was a paper where he stated this idea. So quantum mechanical experiments can be complicated and require a lot of resources and investment to implement them. But now we can imagine that our quantum computer can simulate quantum mechanics. And so instead of making a costly experiment, we may just simulate it on a quantum computer. So we obtained just the same output as would have been on experiment. In upcoming notebooks, there will be explanation also why 2 Hadamard gates returned our qubit to state 0. So your question will be answered soon. Why it is perfect? Because this is how the simulation here was defined. You have seen for probabilistic operations, we had vector matrix multiplications. You will see after a few notebooks today how mathematically our quantum computation is defined. So basically, processes in quantum mechanics have been described quite well with mathematics. And so our computer is able to manipulate mathematical operations and mathematical objects. And this is how the simulation works. After a few notebooks today, you will see more exact explanation about how it is described. And this is why it is perfect. Like simulation is computing what should have been obtained as expected outcome. In reality, real quantum computers may not be perfect, and so these operations or measurement can be performed with errors, and then we would obtain some different statistics. It was also mentioned in last notebook from yesterday with first quantum program. So I guess somewhere here. Because I remember, yes, there was a mentioning that on a real quantum device you may have a bit different outcome. Yes, here. So on real quantum computer, these executed experiments, we obtained not so perfect result. We still had state zero with probability roughly 6%. So real quantum devices are not perfect. Simulators are imitating perfect conditions. So here is task one, the only task in this notebook, where you need to repeat first and third experiment. So you might do a lot of copy pasting when implementing the code. So idea is to now try the same experiment, but when you start not from state zero, but from state one. And to see what happens if you apply 1 or 2 Hadamard gates and do the measurement. You remember from previous notebooks that we can get state 1 if we apply X gate. So you need to perform the same experiments, but you need to apply X gate before Hadamards. So this is a task that I will leave to you. After the lectures, you can do it. So at the moment, you have seen that this shows us a bit how in quantum programming we can represent some of the experiments and how circuits can look like. And now step by step we will have explanations. And first we start with a qubit. So quantum systems are linear systems, and we can represent them states with vectors and quantum operators with matrices. And new quantum states are calculated corresponding to matrix vector multiplication. So exactly what we have seen with probabilistic computation. So this is exactly answering some of your questions. So quantum mechanics can be described by linear algebra as vectors, matrices, and multiplication. So we already used two vectors, and the representation is quite similar. So you see for state 0 and for state 1. We have two-dimensional vector stating that state 0 here will have amplitude 1. I will soon explain you also what does this word mean. So not operator. We remember that it is also a classical operator. It is reversible, so it is also possible to use it as a quantum one. So this is how it looks, X gate. As you remember, state 0 becomes state 1 and state 1 becomes state 0. And here you see explicitly matrix vector multiplication. So this is basically what happens in your simulator. So simulator is exactly, has at the beginning state 0. So you have this vector. Then you ask to apply X gate, this one. So computer calculates vector matrix multiplication. You obtain this output. Here is a short explanation why not operator is called X gate. In short, if you have also complex numbers, it can be represented as rotations on a Bloch sphere, and X refers to rotation around X-axis. This is just extra information. Don't worry if you are not familiar with Bloch sphere. It will be very well explained in next course, which is called Silver, which we also organize regularly. So there is always something to look forward after you finish QBronze workshop. So we have seen X gate. How about Hadamard gate? Hadamard gate looks similar to coin flipping, and this is how matrix represents it. So there are some differences from classical systems. First of all, we can have negative entries, this one. And second, instead of 1/2, we have 1 divided by square root of 2. So turns out quantum systems can have negative transitions. And we will see then how it looks if we do vector matrix multiplication. So if we apply Hadamard to state 0, we obtain first column. So this is what we get. State 0 and state 1 both have value 1 divided by square root of 2. But as you remember, when we do measurement, we have probability 1/2. So how can it be possible? Explanation comes soon. So if we start with state 1 and apply Hadamard, what we get? So when you will do experiment, you will notice that you will also get state 0 and state 1 with equal probabilities. But corresponding to matrix vector multiplication, this is what we get. 1 divided by square root of 2 for state 0 and minus 1 divided by square root of 2 state 1. And still both of them give us probability 1/2. So here comes the idea. So when quantum system is measured, probability of observing one state is square of its value. There's only text on this page that is highlighted so much. And then this value is called amplitude. So basically in this experiment, you have state 0 with amplitude 1 divided by square root of 2, state 1 with amplitude minus 1 divided by square root of 2. If you take square of these values, you will get the probabilities. And you will get 1/2 for both of them. So these are amplitudes, and probabilities will be 1/2. Here is one more remark, that after we did the measurement, our system collapses to the state that we have observed. So if we measured state 1, after that, our system will remain in state 1. So you have seen what are the states when we apply Hadamard to state 0 and state 1. And they respectively are denoted as plus and minus states. You see, like we have equal probabilities of both of them in both cases. But in first one, we have plus sign, and second one, we have minus sign. This is why they are referred to plus and minus states. So here's task 1. It is not about advantage, it is mostly about the underlying physics that happen. And so square of the absolute value was the way how it actually behaved in nature. And you will see another example with square of value later, I guess also today. Currently, just you can think of that this is the behavior that has been described mathematically only through square of absolute value. No, I'm not 100% sure how it exactly is justified, but I can give you example of gravity. There is a formula that states like how much two different bodies with masses are attracted to each other. And we know that gravity becomes weaker the further is the distance, and it is quadratically proportional to the distance. So like if you are 2 times more away from the object, the gravity effect on you will be 4 times smaller. So this is like one of the examples where we also have square of the value. I see a hand. You can unmute yourself and ask question.
Maxim, I don't know if maybe I could help a bit with the historical context
Okay.
about the way it is squared. So when they started, like in the beginning of quantum mechanics, you have the Schrodinger equation that maybe we're going to see maybe some reference in the next days. But then the Schrodinger equation is basically like you solve the equation and the solution of this equation is the state of the particle, that here we have like 0 or 1 as the state. And they don't really knew how to, how they should interpret the solution. Okay, it works, but what physically it means that the solution is this value. And so one of the proposals to explain that was given by Max Born when he made a analogy between quantum mechanics and optics. And in optics, you have the electric field associated to a wave. And it's well known experimentally that if you take the square of the electric field, what you obtain is the intensity of the wave in a given position. And so he thought, well, maybe we could make the same association and take the square of this solution of the Schrodinger equation and associate it to the intensity or the probability that that the given result will be obtained. And so this was his proposal, and it was experimentally observed that this is the case. So it was originally as an analogy between quantum mechanics and optics, but which eventually became experimentally supported. So that's how it came to be the square of the solution and not the solution as being associated with the probabilities of your outcome.
Oh,
yeah, and it's called the Born rule, as someone posted in the comments.
Thank you. That was great explanation. Yeah, this is one of the aspects that I like about the workshops. So if you have ideas or explanations, you can always also contribute. And you know, even it is possible, maybe in future, some of you would be also interested to contribute to material developments. I'm pretty sure we would like also to have a bit extra courses or explanations exactly about quantum mechanics. So this is something to keep in mind. How do we run Qiskit on an actual quantum computer? So sadly, throughout the course, we won't be doing it explicitly. It's first of all maybe very time intensive, like it depends on your access possibilities, you would need to register. But let me just see what it will open now. They change their interface quite frequently, and they have my access somewhere stored, but basically you can register here. It is possible to use their simulators or real devices where you can design a circuit just as a diagram here. And it is also possible to get access, which will give you a token, and you will be able to submit your code on their real device. So in short, this is how it works. You get the access. And so, yes, as I said, we are not running all this code on a real quantum computer, but only on simulator. But the good thing is that all the same code will work also on a quantum computer as well. So you're able to submit it to their devices. They have limited capacity, and also you might need to wait a small queue, like several minutes or 1 hour before your code gets executed, and then you will get outcomes. But yes, it is possible, it is available. And what you will learn throughout this course, all this code can be run experimentally also on their devices. So I guess you will have no difficulties with task 1. Just for warm up, what are the probabilities for this first vector? So if we have such quantum state with such amplitudes, what will be the probabilities to get state 0 and state 1? Please write in the chat, and meanwhile I will react on the question. Yes. Yes, you are correct. You answered the question for all. Thank you. So is there a way to run Qiskit on an unknown device many times and find out? This is very fun question, actually. Glad you asked. So the question is like whether it's possible to run Qiskit on a known device many times and figure out whether it's a real quantum device or just simulator on a classical hardware. It may be tricky because there were legends, maybe IBM is actually just simulating noise. So I guess there are some techniques that might have better prediction to catch that it was not a real quantum device. But in general, it is actually quite hard task to distinguish different probabilistic outcomes. No, idea is like ideal simulator will not make error, but it is also possible to simulate possible errors. And then in such case, it would be hard to distinguish. But in current case, your simulator will give perfect answer and quantum computer will have at least some slight error. But quantum computers are improving, maybe in future errors will be mitigated. So about quantum state, what we learned so far? It is represented by vector. It can have even negative values. And so amplitude can also take any of these values. And probability is equal to square of the amplitude. And next, now more information about quantum state. As we know, overall probability should be equal to 1 to observe a quantum system. So summation of probabilities should be equal to 1. So here are some examples. These two states here are not valid quantum states. And here is the reason, because summation of squares is not equal to 1. So therefore, this is what we learn. Summation of amplitude squares must be 1 for a valid quantum state. And here is more formal definition. Not definition, but idea. Quantum state can be represented by a vector having length 1. And now it gets interesting when we speak about quantum state of 2 dimensions, which is representing our qubit. So suppose you have 2-dimensional plane, and these numbers can be our coordinates. So these are our coordinates, 1/2 and 1/2. And what will be the length of the vector if we have length and height being x and y? Then total length of the vector will be square root of summation of squares. Summation of squares is actually summation of our probabilities, and it should be equal to 1. So for real quantum state, it should be equal to square root of 1, which will be equal to 1. So this is why we state that quantum state can be represented by a vector having length 1. And it will be the case also for larger systems with more than 1 qubit. Summation of amplitude squares gives the square of the length of the vector. This summation is 1, and so square root is also 1. This is why term length is used. So here are additional technical notes. How we also get this number 1 representing length. It can also be represented as inner product. So now we have the following vectors. I will ask only for first question from task 1. What should be the value of A in order for such vector to be a valid quantum state? So please think a bit. I give you 1 minute. So what value A will satisfy the property of valid quantum state? And by the way, I didn't react. Answer to last question on previous task was correct. Wow. You already provided both possibilities. So there is also one more answer on 0.7. Good. So summation of squares will be 0.01 plus 0.09 plus 0.16 plus 0.25. And so we'll get 0.51. 1 minus 0.51 is equal to 0.49. And square root of 0.49 is equal to 0.7. So this is what you obtained. But there is one more answer. Indeed, minus is also working because minus 0.7 squared is also 0.49. So therefore, this question had two answers. Yes. All right. So now about quantum operators. So valid quantum state should always have length 1. Therefore, quantum operator should still keep quantum state, correct? And length preserving square matrix is a quantum operator. So this is our Hadamard operator. And the task here will be to generate random but correct quantum state. So summation of squares of amplitudes should be equal to 1. And then here you would be asked to manually create the state, random one, check whether it is valid. So summation of squares equal to 1. Then multiply Hadamard operator. So you will get new state and check whether the new state is also valid. And then there is a task 3 that asks to prove it mathematically to show that indeed it also will be valid quantum state. So this is what you will be able to play around after the lecture. But yes, this is currently the information about quantum operator, that it should be length preserving one. So I guess this will be, okay, we'll go through one more notebook before the break. How to visualize a real valued qubit. So you remember we can have also negative amplitudes. So let us pick 4 different states, 0, 1, -0, and -1, and draw them as coordinate points on 2-dimensional axis. Then this is what we get. You see, on the left side we have state 0, on the top we have state 1, then on the bottom we have state -1, and on the left side we have state -0. So here you can also draw them as vectors, as arrows. And now the question is, so if we use the function written in the previous task, where we generate random quantum state, you remember that this is vector with length 1, and it can be random. So how would look our state if we created 100 random states? So like how they would be arranged on our two-dimensional plane. So since we have center with coordinates 0, 0, and we can have vectors with distance 1 only, and we can have arbitrary combination of x and y coordinate. But the thing is that length should be still equal to 1. So then, this is what we get. So if you have all different possibilities of vectors with length 1, if they're all pointing in different directions, at the end you will get a circle with radius 1. And basically, there is idea of unit circle. So all real-valued quantum states of a qubit form the unit circle. Length of each quantum state is 1. So all points are 1 unit away from the origin of circle, which has a radius of 1 unit. So here is our program function written in Python that we can use in upcoming parts of materials. So here you can see this is our unit circle. So all possible points on surface has distance 1 from the center. And so any possible state will be represented as vector pointing on one of the points on this surface. So let's see examples. Suppose that we have single qubit. It is with real numbers and of 2 dimensions. So it is vector from origin to that point. And then we draw the quantum state, which has state 0 of amplitude 3 divided by 5, and for state 1, 4 divided by 5. Then this is how it looks. So coordinate x is 3 divided by 5, and for y it is 4 divided by 5. And we can draw projections here. And now trigonometry comes into play. So we have length equal to 1. How to calculate the lengths of vertical and horizontal parts? And this is actually what we get. So if you remember trigonometry, then if you know this longest side and you know the angles, that you can calculate the lengths of the vertical and horizontal sides as well. So it is equal to cosine of angle A and sine of angle A. So you see, we can have angle from state 0. So we have state 0, we have our vector V, and this A is our vector, our angle for the vector. It is equal to A, and if we know this angle, then we can calculate amplitude for state 0 and amplitude for state 1. Correspondingly, from these amplitudes, we can take squares and calculate the probabilities. So you see, actually it is possible to define real-valued qubit just by single angle, because it is all that we need to reach any point on this surface. So the angle of the vector usually is in radians, and radians, short explanation is that full circle is equal to 2 pi, which is equal to 360 degrees. According to geometrical formulae, if you have radius 1, then length of all the surface will be equal to 2 pi. What is important now to remember is that it is angle from state 0 counterclockwise. So you see the direction. So starting from here and going to here. This is the angle that we're speaking about. So here is a code that will generate it randomly. And here are all the calculations done. So for example, now we have generated 164-degree angle, which is 0.45 of full circuit multiplied by 2 pi. This is how many radians. And here are amplitudes for state 0 and 1, calculated as sine and cosine. You can even see it in the code. And then probabilities, and summation of probabilities should always be equal to 1. So another example here. So you see, basically, we can generate arbitrary quantum state. We see the probable amplitudes just by picking angle. So any quantum state is a point on unit circle, and we can use this fact to generate random quantum states by picking a random point on the unit circle. For this purpose, we just pick angle between 0 and 360 degrees and then find the amplitudes. And this is what is asked in task 3. I got here error only because okay, I guess it's because here we have a function that doesn't have any continuation. But basically, yes, this is the task where you need to try to generate your quantum state, but now instead of picking two numbers and normalizing them, now you just need to pick arbitrary angle and then calculate the amplitudes from it. Please let me know if you have any questions. After that, we will have a small break and continue with remaining notebooks and quiz. All right, so then I think we can start with our break. So let's continue. I even gave you one more extra minute probably, and at least I see that people didn't leave. This is good. So we will continue with superposition. Classical case, there is no counterpart to the concept of superposition, but we may get classical analogy to give us some intuition. So you remember about our probabilistic experiments, probabilistic coins. And you remember our probabilistic operator from coin flipping game yesterday. So Isa starts in state 0, and then she applies this operator. If she does it secretly, so means she has tossed coin, but we didn't see the outcome. All that we have is information about probabilities. And we see that probability of state 0 is 0.3, for state 1 is 0.7. So Isa has either state 0 or 1. But for us, from our point of view, she has 0 with probability 0.3, 1 with probability 0.7. So we can think that your state is in probability distribution of state 0 and 1 with some weights. Weights is like amplitudes. In this case, it is probabilities. But when we observe the state, then it becomes deterministic to us. Then we're 100% sure that it is either 0 or 1. So we can think of that when we didn't know the outcome, this is all information that we have. So we have probabilistic state. When we observe it, then we will see deterministic outcome, state 0 and state 1. And this is something similar to what we have in quantum system. We'll have superposition, which will be in reality something between 0 and 1. And when we do measurement, observing the state, it will collapse either to state 0 or to state 1. This is why this analogy has been used. What is the difference? In classical case, it's already at this point will be 0 or 1. Because our coin has been landed and it is already predetermined whether it is 0 and 1. In quantum case, it will be like if it is stuck between these two probabilities, and only when we check it by doing measurement, we'll get 0 or 1. So this was our third experiment, and now let's see vector matrix multiplications. So at first step, we get this state, like we have seen before. So another way how we can represent it is like this. So we have state 0 with amplitude 1 divided by square root of 2 plus state 1 with same amplitude. Now we apply Hadamard again. According to linearity, we can also do it separately on each of the parts. So here you can see Hadamard to state 0 will get us this state. Hadamard to state 1 will get us this state. So if we calculate separately from our this state, applying new Hadamard, then this is how we can calculate it. So you see, we apply Hadamard to our new state, and it is the same as keeping amplitudes and applying Hadamard separately to state 0 and state 1. And this is what we get. And you can notice that we have amplitude still for both state 0 and 1, but if we sum them together, for state 0 amplitude become 1, but for state 1, amplitude became 0 because of cancellation. So after the second Hadamard, our outcomes has interfered with each other. And in quantum case, interference can be both constructive and destructive. Constructive, you see, they interfered and amplitude increased. Destructive, they interfered and amplitude decreased. In this case, it became 0. So in classical probabilistic systems, any transition of non-zero probability, it will contribute positively, but in quantum case, it can also be negative. So without knowing the other transitions to the state, we cannot know what it will be. If it is only transition, then of course, contribution is positive. And if we have more than one transition, then depending on summation of all transitions. So simple rule is, if final amplitude of the state and non-zero transition have the same sign, it will be positive contribution. If signs are opposite, then it will be negative. Like here, we had plus and minus for state 1. You can think of destructive interference as example of noise cancelling headphones. You have sound wave and you have the opposite sound wave. So like one of them goes like this, another one goes on the opposite amplitude, and the result will be silence. There is no wave. So intuitively, it's something similar to this. So in task 1, you are asked to do the same calculations, but now for the case when we start in state 1 to observe constructive and destructive interferences. But basically, this is one of the explanations why at the end we have observed state 0. So after applying Hadamard for second time, all amplitudes got to state 0, and for state 1, amplitudes have been destructively interfered. Overall, quantum system can be in more than one state with non-zero amplitudes. In such case, we say that it is superposition of these states. Transitions may affect constructively and destructively, as we have observed. And destructive is happening because opposite signs of amplitudes. Otherwise, all are added up. And now the measurement. So you can measure quantum system, and then system will be observed in exactly one of the states. And this is the most basic type of measurement. There are more generic ones, but they're not discussed in this course. So the probability, as we remember, is square of the amplitude. If amplitude is 0, then state cannot be observed. If amplitude is non-zero, then state can be observed. So for example, for this state, we'll have 0 with probability square of the value 2 divided by 3. For state 1, we get probability 1 divided by 3. And the things that I have mentioned before, where we do measurement, system collapses to observed state. So if we do measurement of this system and we obtain state 0, then this is what our final state will be. Then if we continue computation, we start from state 0. So information in superposition is lost. We get the deterministic state. So here is a second experiment where we had the case that if we measured state 1, we do not do anything. If we have state 0, we will apply one more Hadamard. This is what was in second experiment. So we had two beam splitters, but second one is only applied to state 0. So this is basically how experiment looks like. We have state 0, we apply Hadamard, we get equal superposition. We do measurement. If we get state 1 and it is with probability 1/2, then we stop. But if it would be state 0, we would apply Hadamard again. And we get state 0 and state 1 with equal remaining probabilities. So here on the right side, you can check later. It's more described step by step. But this diagram basically is what this experiment represents, and this explains our probabilities. So you see, since here our system collapsed to state 0, then applying Hadamard again puts it in superposition for 0 and 1. How to implement such experiment with code? So it is possible after the measurement to apply operation with additional condition on the value of classical state. So it means we have measured our system, and if our state of qubit has been measured as 1, we'll apply gate to that qubit. And so here how the code looks like. We apply Hadamard, we do measurement, and then if measurement outcome was 0, then apply Hadamard to state 0 and do measurement again. And this is how our circuit looks like. So as we remember, probability of state 1 now should be 75%. You can repeat this experiment. Numbers may differ a bit, but overall it will be around 75% for state 1 and remaining for state 0. So you see we had Hadamard, we did measurement, state 0 and state 1 with equal probabilities, but for state 0, again, we repeat experiment, and then we get 0 of 1/4 probability only. So this is actually how would this second experiment look like as a quantum code, quantum circuit. And here are several tasks where you need to play around with using this control, not control, but conditional operations. So intermediate measurements, I guess Microsoft are claiming that they already have a quantum computer being able to represent such functionality. So it might be possible that it will appear later. Currently, most quantum devices are operating without this possibility to, during the process of computation, to do measurement and continue the computation. Here it is, this symbol is CIF. I'm not sure actually what kind of if are you thinking. because this is what is actually how it should look like also on IBM simulator. On a real quantum device, it wouldn't be available. Their hardware is not capable.
Can I ask this question on audio?
Yes, yes.
So after the first measurement, it should be in state 1 or 0. But how does the second Hadamard gate knows that it should only be done to the state 0, not to state 1? So in the circuit you printed here on the notebook. Yeah, this one on the picture.
So basically, you see, we still classically write this code. We can use loops, we can use if operators, and so on when we create a circuit. What is the difference here is that this Hadamard gate, it checks before applying it. We check first whether we have classical state 0. And using this value, we decide whether we will apply Hadamard or not. Since classical state is the same as the quantum one that we have measured, then as a result, Hadamard will be applied only if quantum state is 1. Otherwise, Hadamard will not be applied. So it is not checking the quantum state. It is controlled by the classical condition.
Okay, now I get it, yeah.
So here you measured classical state, and here you check what it was, and if it was 0, then you apply Hadamard.
Okay, that answers my question. Thank you very much.
Yes, you're welcome. And thank you for asking. So yeah, basically the remaining part of the notebook is just trying different experiments where you, for example, repeat for multiple times this construction. This is the only place in the workshop where we will use this conditional operator, except there is one more proposal, let's say, where you can try it. So currently think about it as extra, but this might become in future indeed something realistic. One last remark, I have answered the question, but still, what is the difference? It is possible also to have, like, in general, like when you build a circuit, you could write something like if 1 is bigger than 2, then apply this operator. Of course, then it would be false and this wouldn't be applied. Or you did some computation like, and then if x is bigger than 2, applied. So such constructions are allowing you to generate arbitrary quantum circuit by using classical operations. But this one is conditional mid circuit operation. So you do measurement and you still can apply operations after that. So this is trickier to implement from technical perspective. This is why initial IBM quantum devices didn't provide it. Yes, and thank you for sharing, Zaki. All right, we have learned something about superposition, measurement, and here we have seen that you can visualize quantum state as a vector on unit circle. What kind of operations can we perform with our qubit? This is the next notebook. So suppose that we have state 0 and state plus. So we have some operator m that we started from state 0, applied operator m, and we have obtained state plus. If we would apply operator m once more, what can be the next state? What do you think? So please write in the chat, what could be the next state? So we started in 0, we applied m, we got state plus, we apply m again. What can be our state? All right, one of the proposals is state 1. 3 people proposed it. Okay, it is reasonable. It could be. Any other ideas? Oh, okay, state 0 also. For state 0, I guess you also got this idea from our Hadamard experiments here. So when we have state plus and applied Hadamard to state plus, we get again state 0. So you have two possibilities where you get state 0 and state 1. How can we classify geometrically both examples? So we start at 0, we get plus, we get 1 after that. What kind of operation it could be geometrically on a unit circle? Okay, so this evolution looks like rotation. And if we get 0, then plus, and then back 0, then how we can call it? All right, and sadly I have clicked other notebooks, so this might give also a hint. But yes, basically idea is that one of them looks like rotation, another one is looking as a reflection. Why reflection? Because when you repeat reflection for 2 times, you return to initial state. So similarly, we can think here for state 1, and then we get state minus. So what could be the next state? If we start at 1, then we get state minus. What could be the next state, according to our previous ideas? Minus 1 is 0 and 1. All right, so let me correct you. 1 can be, if you do reflection, yes, this is what I raised, and minus 0. So basically, if we do rotation, we go here, and then we go here. So we get minus 0. And if we get a back state 1, then it looks like reflection. 6 pi divided by 4. Not quite. Actually, it would be pi, because it is half of the circle. But yes, rotation by 6 pi divided by 4, if you get state minus 0. So it is possible to initialize qubit also in Qiskit in random state. You remember we did rotations and angle between state 0 is denoting our state. So if we have angle theta, then state will be cosine theta sine theta. So general representation of our state. And Qiskit has so-called RY gate. The only thing is you need to multiply by 2 rotation angle. Here is technical explanation why, because Qiskit is operating in terms of block sphere, and we are now working with real valued circle. So currently just you can think that this multiplication by 2 is technical detail to obtain the functionalities that we need. And this is how it looks like. So you can apply RY gate to your qubit, in our case qubit 0, and we do rotation by specific angle. In this case, it is 2 times our angle. And this is how we will obtain our state. So if we do rotation by 2 pi divided by 3, it is 120 degrees. We provide 2 times this angle to do a rotation. So we have 120 degrees on a unit circle. So to show you, this is our unit circle, and 120 degrees will lead to somewhere here. So you see state 1 is much closer than state 0. And indeed, if we do measurement for such qubit in such state, we'll get state 1 with probability 75%. And so here just, this one is done purely in classical code to show what happened in our quantum circuit. We have obtained the state minus 0.5 state 0 plus 866 state 1. And probabilities are 25 and 75%. And this is how it looks. So, and here will be task where you need to pick randomly angle. So without checking this angle, you would need to do measurement of these copies and then see what are the probabilities for having state 0 and state 1. So just to play around. But basically this notebook is about generating random quantum state by using Qiskit functionality. So you provide a random rotation angle, and in such way you can obtain any state. But also you will see we'll have rotations as operators, and so this Ry gate can also be used to apply rotations on our qubits. But it is also, as I have shown you, very good tool to initialize arbitrary quantum state. You just provide the angle that you needed, you do Ry rotation, and so here we obtained our qubit in this state, basically. Now about rotations. So if we start in state 0, apply rotation, get state plus. What will be our next state if we do rotation? So related to question from previous notebook, but this time we know for sure that it is rotation. So 0, then plus, we do one more rotation. What will be our state? Our state will be 1. Exactly. And here is example how rotation matrix looks like if we do this rotation, pi divided by 4. And matrix is similar to Hadamard operator. You can see we have minus sign, but this time on top. And this is in general how this matrix has been calculated. So if we repeat rotation for 7 times, I will just use the solution to show you how the rotation will look like. This is what you will get. You will need to write the code by yourself. But you see, we do rotation for 7 more times, and each time we draw it, we'll get the whole circle divided into 8 vectors. Now I will finally answer the question about revealing the probabilities from our simulator. It is possible to read the quantum state of a circuit. It is not possible on real quantum device because only way to access the state is to do the measurement, and as you have seen, if we do measurement, we lose superposition. But when we work with simulator, it is also possible to see what is the final state before the measurement that we have obtained. For this purpose, you can see we will use different backend called state vector simulator. It reads the quantum state of the circuit at that point. So it is a classical simulator, and we will get the distribution of amplitudes of our states. So basically, this is the code that is needed. And then it is possible to print amplitude of any of the states. Here we use real because they can have also complex component, and it may look a bit overwhelming at first. Optimization level, we usually set it to 0 because Qiskit may optimize gates that you have applied, trying to have it more optimal. So he might, for example, remove some of your gates, and then final outcome may be a bit different. I mean, if you put optimization level 0, then your simulator or real quantum device will do exactly what you have asked. But in purpose for saving the resources, if optimization level is not 0, then it might be the case that there will be fewer operations applied. Yes, you're welcome. So here we have task 3, and we need to apply the gate. I will again allow myself to show you the solution, but not the code itself, but the outcome. So here you're asked to use state vector simulator. Okay. Sadly, I cannot get it. But I will just then do it in old-fashioned way, print. So you see, I actually had to update my Qiskit. All right. I will not be able to show you, but I'll try to open another notebook that I have used very recently. So this is basically how it can look like. So you can print quantum state of your state vector, and it will show you amplitudes for your states. This was example where I had also complex numbers, but basically this is complex number corresponding to state 0, this for state 0, 1, this for 1, 0, and this for 1, 1. So you can output the amplitudes of your quantum state that it has before the measurement. And as you know, squares of the amplitudes is our probability. Well, I don't have direct answer on this question, how to optimize the gate error energy of the Hadamard gate. I thought it is mostly related to the hardware, how it implemented it. So it might be hardware specific to optimize the gate error energy. So yeah, basically here you will be asked to apply a Rai gate and use the state vector simulator. So this is the general operation of rotation. If you rotate by some specific angle, then this is how the matrix is formed. And theta parameter is rotation in counterclockwise direction. So here you can play around what happens if you do rotations for several times in specific direction. And then you will see in which cases it revisits state 0 and which case it isn't. This is just related to what number is multiplied by pi. For irrational one, you will notice that it will never reach. In such case, you will see that after 12 times, it will return exactly to state 0. This one is about the dot product of two quantum states. So I also currently keep it as a practice for you in future. If you will have questions later about this, then definitely ask me. So this is just to show you some interesting relation. So if we have two quantum states that differ by angle pi divided by 2, what will be mathematical property of those? And it is partially related to distinguishability of different quantum states, but I will not tell more until you will try by yourselves. And last task here is also to play around with randomly picked qubit. And then you will have it being rotated by theta or theta minus pi divided by 2. And here even you given hints that you're allowed to do one more rotation and do the measurement. And then the question is, can you determine the angle and whether can you distinguish between theta 1 and theta 2? So these tasks from 5, 6, and 7, especially 6 and 7, just for you to give more opportunity to play around with rotations and then to try to analyze whether you can, from measurements only, get any idea of what was the initial rotation angle. Why it is important? Because, as you have already heard today, only way to get information about quantum system on a real device is to do measurement. And so here, we're basically trying to get some information about our states from the measurements. But overall, this concludes the notebook about rotations. Now we'll shortly speak about reflections. So one of the reflections is called Z gate. Again, letter Z is similarly to letter X related to the axis on a Bloch sphere. So identity operator looks like this. You remember it from the very first notebook. It doesn't affect the computation. Z gate is very similar, but the last entry here is -1. So if we start in some state like this, in final state, amplitude for state 1 is multiplied by -1. So you see, second number here is multiplied by -1. So this is how it looks if we draw two states. If we apply Z gate again, we will return back to initial state. So we can think of Z gate being a reflection over x-axis. If we apply twice, then we do not have any change because it is a reflection. If we apply it once, we see it just gets on the opposite side from the x-axis. And so here is a task where idea is to apply Z gate between two Hadamard gates. So you have noticed here that Z gate does not affect the probability at the end because we just multiplied amplitude by -1. And plus and minus will have the same amplitude probabilities. But at the same time, this difference in amplitudes is affecting computation in general. And here you will see that if you apply Hadamard gates and between them Z gate, it will affect the outcome. So outcome with and without the gate will be different. This is why you are asked to play around here. What about Hadamard operator? It doesn't look like a rotation. It more looks like a reflection because you remember if we applied it 2 times, we get initial state. Hadamard to state 0 get plus, apply it again, you get state 0. Similarly for state 1. So it looks like reflection. This is between state 0 and plus. This is between state 1 and minus. So geometrically, this is the line of reflection for Hadamard gate. So it turns out Hadamard gate is a reflection, and this is about which plane reflection is happening. So pi divided by 8 is the angle of this reflection line. In task 2, you are asked to play around with random quantum state and applying Hadamard gate to see how these reflections look like. In task 3, you are asked, what is the matrix that represents reflection over the line y equal to x? So let's look at this. You see here, it is line where x is equal to y. So this is our reflection. Does it correspond to any familiar operation? To analyze it, let's first assume that we are in state 0. And if we do reflection over this axis, what will be our final state? So state 0 reflected over this line. While you're thinking, I will remind, okay, so there is proposal 1, at least already by 3 people. And you're correct. So this is how it looks. You can think of mirrors, and reflection should be on the same distance, and angle should be the same here. So we have here perpendicular angle and at the same distance. So therefore we get from state 0 to state 1. And if we're in state 1 and apply this reflection, we'll get back to state 0. What was operator that takes 0 to state 1 and 1 to state 0? Did we have seen such operator before? Good. So your proposal is not operator. And let's see what we have in materials. Indeed, not operator is our X gate. In other words, that is reflection over y equal to x-axis. The operator was reflection around x-axis, and Hadamard was reflection over this line. So you remember where we have pi divided by 8 angle. And arbitrary reflection can be represented like this. So in previous notebook, you have seen general formulae for rotation matrix. So this is rotation. If you want to do rotation by specific angle, you just need to put theta here. For reflection, we have this one. The difference is here we have 2 theta. This because of geometric properties. So Qiskit doesn't have reflection operator. We have shown you how you technically can use a rotation operator here where with using RY gate. This was even not here, but one notebook before. Okay, this was solution. So this one, RY gate. And for reflections, there doesn't exist specific gate, but it is possible actually to implement it. And this is why we have here extra task. So rotation reflection matrices have some similarities, and you need to try to represent reflection matrix as a combination of basic reflection operators like X, Hadamard, or Z-gate together with rotation operator. So it is possible to represent reflection through rotation operator with some additional reflection gate. And here is about randomly creating reflections. Both tasks are extra, but you might be entertained when you try to solve them. So now we have seen some additional information about rotations and reflections. And it turns out most of the gates that we have seen so far are reflection gates. So we have one last notebook left. There will be not so much information because it is again task notebook, and this is probably the one that you will spend most of your time. I mean more than on any others. So there is a simplified version of quantum tomography given here. So it is similar to learning the bias of coin by collecting statistics. You remember you can toss the coin and we can see ratio between obtaining heads and tails. Here we will do measurement to guess the amplitudes of our quantum state. The thing is that making only measurements is not enough. You have seen that there are cases where we cannot distinguish between two cases because probabilities will be the same. And this is example given here. So for both these states, you will have the same probabilities because they only differ by minus sign, and minus squared will give you the same number. So therefore, sometimes you are not able to distinguish between two states when you only do measurement statistics, because measurement probabilities can be the same for different states. I can give you one more example. So for this state, also this state would provide the same probabilities, because you see they will have same amplitude for state 1, and for state 0, their amplitudes will differ just by minus sign. So we assume that you have 1000 copies of some qubit, and your task is to learn the state of this qubit. So if you do 1000 measurements, you would get some probabilities, and so you, by the statistics, you can assume what are the amplitudes. But as I have shown you, there will be cases when you cannot distinguish between two different qubits. So here is some functionality given with descriptions. So you will have unknown qubit, which will be generated as a random angle between 0 and pi. And you will be able to get qubits, to measure them, and also to rotate and compare the guess of your outcome. So here is your class. So we have 1000 available qubits. You can get qubit to work with it, you can measure, and you can do additional rotations. So you see, your task will be to use these operations. And here are examples how to use these operations. And your task will be to guess the angle theta that is hidden from us. So by measurement, you can get some statistics, but still you remember that for some states, measurement outcomes will be the same. And here is example, if our theta is pi or 2 pi divided by 3, for both of them, you'll have identical probabilities and so measurement outcomes. So then you won't be able to distinguish between these two states. So only measuring all qubits doesn't guarantee the correct answer. This is why you're asked to test your solution at least 10 times, because you'll get at least once that you guessed incorrectly which one of these two. To change this, you might need rotations. As you have noticed, we have also rotation operator. So this is quite creative task where you need to think about how you can distinguish between different states and how you can get amplitudes from your measurement outcomes. So this combines previous knowledge that you have obtained. And there are also extra tasks. One of them, if you work with two different qubits, and whether there you would be able to distinguish as well. Keep in mind that if you have two qubits, you will have 4 different states: 0, 0, 0, 1, 1, 0, and 1, 1. So it might be a bit more complicated. And last is discussion. So this is what I will comment now on. So what if we wouldn't restrict us between 0 and pi, but up to 2 pi? Then whether it is possible to distinguish them in all cases. And it turns out that there are difficulties if state is only differed by minus sign. So whether it is possible to distinguish between 0 and minus 0, even if we do some rotations or reflections. If we do measurement, we obtain both states with 100% probability and you would get just one. Minus is not counted. What happens if you perform some operations? So all 1-qubit operations are 2 by 2 matrices. So if you apply sequence of operators, you can think of one matrix representing multiplication of all these matrices. By linearity, if you applied matrix and obtained some state, and you applied matrix to the same state but with minus sign, the outcome will only differ by this minus sign. And measuring both these new states, both of them will have the same measurement probabilities because minus sign is not affecting. So although these two states differ mathematically, they are assumed as identical from the physical point of view. And this minus in front of the state is called global phase. In general, global phase can be complex number with magnitude 1. Currently, since we work only with real numbers, the only example of global phase is minus in front of state. So I want to remark before you get confused, this is global phase, but there also existed minus when we worked with Hadamard gate. You remember this one. This is physically distinguishable. You are able to perform some operations to distinguish between this and this. Because here, minus appears in front of one part of the states. In this case, in front of 1. In case of global phase, it is minus that is in front of all bracket, of all our vector. So about no cloning theorem, it is not possible to clone unknown state. Here, we have state 0 in the beginning always, and we generate 1000 qubits. And to each of them, we applied the same operator. In this way, we obtained 1000 copies. Yes. Yes, no problem. I also answered it in written form. You may have later questions about those. First of all, our next lecture will be only on Saturday. So you have the today and also whole work week to work with the notebooks, and probably you will have questions. And so, of course, when you get such, you can ask in our chats on Discord. So don't worry if you will have such. Probably you will have, because some of these tasks are a bit more complicated. This one, indeed, as I promised, it is interesting to think about how to distinguish between these two cases. So let me know if you will have more questions now. After that, we will do quizzes. It will be short, it will be just entertaining, but also it is a very fast way to check yourself. How did you understood last topics? Thank you. It was done intentionally to have less math, and we still have a lot of suggestions to lower amount of math even more. So this course can be simplified, but without complex numbers, it's already much, much better. And by having this introduction, later transitioning to complex numbers also is much easier. So let's say I didn't learn linear algebra and I learned quantum computation and quantum programming. And after that, I learned necessary information from linear algebra. So, but basically many courses start exactly with linear algebra, and those who don't feel confident in it, it becomes more complicated. So currently we just use the minimum in order to be able to program something useful. Yes, we will not need complex numbers for Grover algorithm. This is exactly example where knowing just basics and this main gates is enough to implement Grover search. But also fun things that you will see analogy with rotations and reflections when we will explain Grover search on last day. So I will switch then my screen to the Discord. Thank you for kind words. Quiz. Maybe somebody we'll start quizzes here. And first one will be just to give you technical preparation so you get used to how it works. I hope it will work from the very beginning. I guess when creating the server, I have invited QuizBot. Here you see him here. And it allows to launch quizzes. So I just remember on one of the workshops I had difficulties that I wasn't able to launch the quiz because there were some permission difficulties to this QuizBot. If it will be the case, I will hope I will solve it momentarily. But basically, this is what we sometimes do on our workshops to entertain participants a bit and also to give them a bit more possibility to work with the knowledge that they have got. So here the questions will appear and you would need to press the button corresponding to the answer. And depending on that, then you will get points. For correct answers, you will get points. So let's try the first one. This is example quiz to get used to. I don't know why it's not working. Okay, so functionality changed, I guess. We need now to write it play. I hope it is like this, 3410. So you see from last workshop, functionality changed. This is not cool. It says me that quiz ID didn't found. Okay, this one works. Sadly, you will not have practice. You will need to already answer the question. So here you see, you have question, which one of the following classical operators is reversible? Not 1 and 0. And you would need to click these numbers here. Yeah, I totally agree with you about immutable. So please click, you need to click the numbers. So for example, let me Okay, and then it shows which one was correct. And you see some people answered correctly, so first 10 people. In past quiz looked a bit different, but I'm glad it's working. Yeah, you remember, we used Hadamard as coin flip. Oh, so I see 25 people participated, 26. And who got the first place? Nice, congratulations. So we will have one more quiz in a minute. Yeah, I will launch it. But overall, yes, quite good results. And don't worry if you didn't get something correctly, you can check then what was the correct answer. So maybe this will answer on your doubts when you were not sure. And now I will launch the second quiz, and after that we will finish. If I recall correctly, this quiz will have a bit longer time on questions. So I hope this quiz also exists. So I'm starting in 10 seconds. I'm not sure, it may be glitchy. I remember before buttons and other stuff were implemented completely differently, and it was also glitchy. This time, I'm not sure. But I will try also to click just to test it. Okay, I'm launching the quiz. Good luck, everyone. Okay, the problem is that it doesn't show to you whether the click button worked. I will have 0 points for this quiz. Probably, or maybe I answered correctly, I don't know. Also, you get more points if you answer faster. So this is why there is a different number of points for people answered correctly. So it is a competition. So that's it. I hope it was fun. Did you enjoy it? Huh. I'm 24. Yes, I'm glad to hear. Yeah, quiz is fun, and it's also a good opportunity just to think like in very fast way about the topics that we have discussed so far. They're not perfect, but at least they're fun. All right, then I guess that's it for today. Our next lecture will be on next Saturday, but remember that there is one more meeting today planned after 3 hours, a bit less. No, sorry, not 3, but 2 hours, a bit less. I see just times are different for our zones and I a bit messed up, but yeah. All right, then I think we can finish for today, and please remember that communication Discord is continuous, so whenever you have questions, proposals, requests, complaints, feel free to contact us through the environment. And then I will see you on Saturday, and today also please use the opportunity to join the meeting.